atomic iron and some of the ionized species in this basically star planet, Kelt 9b. So this technique is very powerful through this cross-correlation template mapping for detecting species, detecting absorbers in an atmosphere. So I'm going to skip through this. So we want to go beyond detection, right? We want to move beyond just detection. How do we go from just having molecules in an atmosphere to the things we want to know, their abundances and their temperatures? So how do we actually place this cross-correlation technique, which is way different than classic transmission spectroscopy or emission spectroscopy? How do we place that within a Bayesian framework so that we can do all these things that we want to do? How do we combine that information with low-resolution data? And then the fact that we're dealing with high resolution means we're dealing with a sort of a pain-in-the-butt radiative transfer problem where we have a lot of radiative transfer calculations that we have to go through. And so we need to talk about how we solve that. So effectively, how do we leverage the uniqueness of this high-resolution technique? How do we leverage this cross-correlation coefficient? How do we leverage the fact that the planet is moving and that the planetary spectrum is Doppler shifting with phase? The sort of kind of theoretical hurdle, if you will, is to construct a likelihood function that takes advantage of all of those pieces so that we can put it within this framework so that we can get these ugly plots that tell us what the distribution of planetary parameters are. So, sparing the details, we essentially have to kind of add a couple of things. The most important thing is the mapping between this cross-correlation function, the ones and zeros that you get when moving those two spectra back and forth. How do we map that into a likelihood function that will be able to handle this data, this normalized continuum subtracted flux as a function of wavelength and time? How do we fit that? How do we do a Bayesian analysis on that? And it turns out, we can talk about this more in detail offline, but there's different mathematical mappings that exploit these different properties, and they all depend on rho. This is the cross-correlation coefficient right here, again, between -1 and 1. And they might also depend on some other properties like the variance in the data and the variance in the model. Moral of the story is, we came up with a mapping that takes you from this cross-correlation coefficient to this likelihood function. And so once you do that, then you can apply all of these standard Bayesian techniques so that you can get abundances and temperatures and cloud properties. So how do we do that in practice? So anytime you do something new, you want to kind of check it to make sure it's not, weird. You want to make sure you get answers that are sensible. So we created a fake data set. So what am I showing right here? This is kind of a typical HST spectrum of a hot Jupiter. You might see some water vapor absorption right here. And then we want to see, well, what happens if we were to observe this planet with the very large telescope CRIRES instrument, which has since been commissioned, decommissioned. But we have this high resolution, we have this high dynamic range in fluxes, which is going to give us more information. So we can construct a simulated data set, and we can go through all the tellurium subtraction processes that we need to. Most of what we observe is the Earth spectrum as a function of time. So this axis right here is measuring time. This axis is measuring wavelength. All the lines in the planetary spectrum, so planet flux versus wavelength, those are all Doppler shifted, so they have these diagonal streaks in time. But then you put Earth's atmosphere on top of that, and you put in all the detector doohickeys, you end up with spectra as a function of time that look like this. We can detrend it, so then we end up with this noisy looking thing in the background. This is kind of what I showed before, right? The spectrum that we care about is really small, the features are really small compared to the noise after going through all this detrending process. But an object like this, with these simulated noise properties, would result in this sort of, this velocity space of maybe a 5 or 6 sigma detection of atmosphere, okay? But moving beyond detection, what we want to do then is say, well, what can we actually say in terms of, I know how much water I put in this atmosphere, I know how much CO, I know how whatever else I put in the atmosphere because it's fake data. How well can I constrain that? The answer is we can constrain these abundances pretty well. Kind of the take home right here is that we can constrain with kind of technology we have now, we're able to constrain the abundances of water and CO to a precision that's at least as good as what we can do with the Hubble Space Telescope. Okay, and that's from the ground, all right? It's from the ground at high resolution, okay? And so we can also make statements about the thermal structure in the atmosphere. So because now we have this, we can answer those same questions about climate, composition, tying that back to formation and chemistry that we could with those space-based platforms with a Hubble Space Telescope.
Hey, Mike.
Yeah.
Hey, I know you're running out of time, but so those error bars on CO are really small, and so is that information coming? So you're combining like an HST like emission spectrum.
This is just it by itself. Sorry. This is just the CRIRES by itself.
That's CRIRES by itself. How do you get error bars like that if you don't know what pressure level you're recording?
Line contrast. If you have two different molecules in the atmosphere, you're so I should have mentioned this. This technique is really good because at your high resolution, you're super sensitive to the line ratios of different molecules.
Okay.
And so that's what allows you to break some of these degeneracies.
Cool.
We can talk about that in more detail
Sounds good.
in the, okay. So we can do some blah blah statistical robustness tests to show that like the likelihood function we came up with isn't completely spewing out nonsense. And we can do these tests to see, well, how invariant are our solutions to perturbations and to random noise instantiation. If we go observe the thing again, are we going to get a completely different answer? The answer is no. Effectively, the mathematical framework that we built follows chi-squared statistics, so everything is peachy there. Instead of fake data, let's talk about some real data. So if we apply this technique on two real data sets obtained with this really narrow high-resolution spectrum from the Very Large Telescope, previously published, right? So these would result, these papers claim, many sigma detections of CO or many sigma detections of water in CO. If we apply this new machinery on that time-varying Doppler-shifted telluric subtracted spectrum for these two real objects, we get some weird answers. So in this particular object, we only get an upper limit on the water abundance, and we get a lower limit on the CO abundance. So it's telling us that CO is there, but we can't say that the entire atmosphere isn't made out of CO. But that would be dumb because it's a Jovian planet. We know the entire atmosphere isn't made out of CO. So this is just kind of letting the abundances kind of run amok and do whatever they want. But this is telling us that we're getting an upper limit on the water abundance, but only a lower limit on the CO abundance. This object has a different flavor. And get a little bit tighter constraint on the water abundance. These blue lines right here are what you would expect given the temperatures and solar composition, which maybe we wouldn't expect that, but just for a reference. We can get a really tight constraint on the CO abundance, but still it's still kind of just an upper limit on the water abundance, and these water abundances in both cases are a little bit lower than what we might anticipate under the assumption of solar elemental abundances and typical equilibrium chemistry. And so just to compare, both of these objects have been observed with the Hubble Space Telescope, and these retrieval analyses have been applied on that low resolution data, and these kind of blue boxes represent those uncertainty ranges. So in some cases they're moderately consistent, but in other cases there's some tension between some of these results. That's kind of the summary right here. We can do cool things because we put this in a Bayesian framework. We derived a log likelihood from this cross-correlation coefficient. We could do fun things by actually combining the high-resolution data, this is what you were asking, with the low-resolution data. So we can actually leverage the power of both, so we can leverage the continuum information that low-resolution data gives us, which gives us sort of an absolute flux level, temperatures, and this high-resolution information, which is really good at giving us the line ratios. And so if you compare those two, so this is, again, a fake data set. If you were to figure out what the range of metallicities and C/O ratios in the atmosphere going through some chemistry, that would be able to explain this spectrum right here, you get kind of a wide range, sort of typical of what I showed before, orders of magnitude values. Because we're only measuring water right here, you can only put an upper limit on the carbon-oxygen ratio. You can't say really what it is. But if you're measuring a region of the spectrum, this K-band right here, where there's both water lines and CO lines, you can break you can kind of break that degeneracy between this metallicity and carbon dioxide ratio that can give you the same water abundance. We can actually get tight constraints on the carbon dioxide ratio. When you actually fit the two together, you can leverage the power of both. In this particular case, you're really kind of leveraging the strength of the high resolution data to pin down the ratio of carbon to oxygen, because you're really sensitive to the ratio of those CO lines to the water lines in this region of spectrum right here. This is for the high-tran people quick. Opacities matter. You get different answers depending on which ones you use. You can tell me if Pokazatl is bad or not. And then, so one of the challenges going forward, okay, this is what we've been dealing with so far with this high-resolution stuff. Really narrow wavelength ranges, okay, but really high resolutions, maybe not this high, you know, maybe on the R of 100,000. But going forward, there's new instruments that are turning on nowish that are going to cover really broad wavelength ranges, all right? And this is going to get even worse when we're talking about next generation of telescopes like the TMT and the GMT and stuff like that. And so we're talking about having to compute radiative transfer, line by line radiative transfer over millions of lines over this broad wavelength range. So we really want to leverage high resolution using this technique over a broad wavelength range because we'll get many more molecules and we'll get more leverage, right, on our constraints. And so the solution basically is, well, radiative transfer is easy, more or less, but the answer is always GPUs, okay? So you can actually do, speed up by about a factor of 400 these radiative transfer calculations, these line-by-line radiative transfer calculations on a traditional CPU. If you run them on a GPU, you can run them much faster. And the reason why you want to run them faster is because you want to be able to put them in this Bayesian framework, into one of these Markov chain Monte Carlos, which require a gazillion calculations, right? And so you can only do that if you're running these things on GPU. Mainly, I just wanted an excuse to blow the rest of my startup money, so it was fun buying these, because now I can play video games all day long. But effectively, I'll stop talking here soon. There's still a bunch of challenges. Lab stuff is hard. We'll talk more about that later. Planets are hard. I didn't even talk about the fact that these planets are 3D, and that's kind of really, it's going to be fun trying to encapsulate